Then we go to the last topic. Uh, Sometimes giving the series is either one of these series given the summation, so you want to recover F. So this is sometimes possible, but not always. Right? And so it's kind of case by case. And the only thing we do is just look at some example to see what we can do for the case that actually can be done. So if you the example for this last topic, 19.1.3. So you want to sum over this. Say you have a sum with all the cosine term and x over n. Right? You want to do a sum. But so this is like a cosine series, or you can say it's or the Fourier series without the sine term. It doesn't matter. So for first, all these cosine are difficult to do a sum, difficult to change it to power. But you realize cosine is just using the Euler relation. It's just the real part of the exponential function. So you can write it like the real part of um, it's e to the I n over n, right? And then e to the I n x, you can reverse the order, I mean, interchange the order and make it e to the I x to the n power, right? And now you have a series, they call it whatever the something to the n power divided by n, right? It doesn't have to be, you know, I mean, whatever the argument is fine. So you can look it up, see if you can find a series that has that kind of form. And the textbook, I think the text suggests that that would be, if I see is minus log 1 minus, so call it z. So basically, the text would say minus log c with this some z over that. Yeah, I think that's what the textbook suggests. Okay, so you can either look up and trust your map table. If you don't like, you can also always do a take expansion yourself, right? Because this function is easy enough, right? So this is taking a Taylor series about zero. This is your function, including the minus sign. So you can always write the Taylor expansion, the f zero. If this is your f, it's zero plus f. Just a few terms to convince yourself that that is truly this form. Prime relative factorial, but derivative, but this is square. Right? See if that is, see if that works. If f is minus log 1 over z, the function, so this is just log 1 over z, and evaluate z equals 0, that 1 minus z 0 is log 1. Log 1 is 0, so that is 0. So that is 0. Right? And f pi obviously is just derivative of this one. You get 1 over 1 minus z and take a derivative of the argument, give you minus sign. So it's but this is f pi. F pi is this one. Minus f pi. So this is f. This is my f. you take the f prime, you get 1 over 1 minus e, and take the argument of this one, give you minus and cancel the minus sign. So this is f prime. Okay, f prime, and then you evaluate at c equals 0. So that gives you 1. That gives you 1. Let me see. F double prime is do the f prime again. So minus 1 over square of this one, and then derivative of this one give you another sign. So cancel with the negative sign. So this is f double prime, but you have a factor of 2. Okay, and evaluate equals 0. So that gives you also 1. Okay, now the triple prime, do it again. So this is minus 2, right? Minus 2, and the cubic power, and can do it derivative cancel the minus. So 1, there's a 2 over, and then this squares also. You see here over 3 factorial. This is 3 factorial. The 3 times 3. You cancel with the 2, you get 1/3. So this term is just 1/2. This is becomes 1/2. And this term gives you just 1/3. And so on. So you can see the pattern now clearly. This is going to here. So this is fine. We check that this is fine. Right. So it's okay. I mean, if you don't trust the table or you forget the table, if you don't have a table, like you have a com, you just do a simple Taylor series expansion and check yourself whether you first guess a likely form function that will give you this series, and do a Taylor expansion to check whether that is giving you the correct formula. Okay, but assuming that everything works out, so this becomes the real part of using this function minus, there's a minus sign. You can do it minus 1 over 1 minus, z it becomes e to no, I forget the log. Minus log of 1 minus log x. That is the form. And now the rest is just to take the real part, right? Now this is a log function, right? So we get the real part. We need to first get the real and imaginary part of the argument of the log function first, right? It's like log. And to get the real imaginary part, just use the Euler formula. Right. And then minus I x. Right. And to get the real part of log function is better to use the polar form, because polar form will give you a product, and then the log will take care of that. The product change to the sum of log. Yeah. The polar form will be the argument multiplied by the phase. The phase will give you a pure imaginary part. Like, so the argument is just the square root of the real part square plus the imaginary part square, and then there's a phase. into the whatever the form, because that is unimportant for us. Because the first factor will give you uh, log of this. That's the first part, and the second part would be just alpha. That is the imaginary part. So the real part is just this one, right? Yeah. I mean, if you like, you can take the square, and then you have cosine square plus sine square be 1. Adding the other one be 2. Is 2. So that to see if that is what the capital is. Minus, that's the I forgot the minus log of 2 minus 2 cosine x square root. But yeah, that's fine. I mean, if you'd like, you can take the square root becomes 1/2. That's fine. That's cosine. That's the property of the log. Right. So that's the example of something that can be done. So you can convert that using the Euler formula, becomes some power. You can take either the real part or imaginary part as whatever the function would be, and then hopefully that power series is you can recognize that to some that is an expansion of some simple function, elementary function. And this one is I pi, right? Right. When you do the log of this product is log of this plus log of that, and log of exponential function give you I phi. Just the argument. Oh yeah, that's passive. Doesn't matter because this is imaginary. This is imaginary. So we take the real part. We take the first part. Okay. All right. So that's just give you an illustration what can be done. All right. So I think that's it for second one. Okay.